Okay, that's right. I've talked to you before about that. Braxton, what is your major? And Chelsea, you can type too what your major is. Okay, so building science at Auburn, business administration, and that's cool, and mechanical engineering. Cool. All right. So today's lesson, in particular, building science or mechanical engineering, it's this we're going to learn a shortcut today that you might in the future need to do, and the reason it well, we'll explain it in a minute. That it's just one of those helpful shortcuts that you might need to use in the future. And if you didn't know that's what that was about, then it would be kind of like weird. Like, what in the world? But it's a wonderful shortcut, and I'll show you in a minute. All right, so today we are finishing up week 14. We're going to, our lecture will be, and it finishes up chapter 7. It's going to be a lecture on how do I write a complex number in what is called trig form. And then DeMoivre's theorem is a way, it's a shortcut that allows you to raise a complex number to a power. And it becomes a very simple way to do it instead of a very long, tedious way. But let's kind of see where we are. Right now, in terms of what we have, our last quiz, and I know teachers say the words quiz and test, and it means something different to them. There's not a standard definition, but to me, our quizzes are 5 questions, and the quizzes don't weigh a lot percentage-wise. So it's like a low risk way of learning to see how well do I understand the concepts that have just been presented before I have to take the chapter test, which weighs a lot more. So we have our last quiz on polar coordinates, and it's due today. So you gotta, if you haven't taken that week 14 quiz, you need to go ahead and take it. Just 5 multiple choice questions on polar, like graphs and conversions, that sort of thing. Not on the complex numbers or DeMoivre's theorem that we're going to talk about today. Then what else do we have yet to be completed? Well, your homework is all going to be due next week on the 30th, which is a Friday. So we have that needs to get completed. Then you have a chapter test next week. I would imagine, because on Tuesday, we'll do the chapter 10 conic sections on Tuesday, and then we'll do the review. So sometime we've got to have that chapter 7 and 10 test. I would imagine, because the review's on Thursday. Well, we'll see. I think ideally it needs to open on Tuesday and close on Thursday. So let's put that here. I'm going to have to put that in because I don't, well, I mean, I could have it going, I could have it the following week, closing on Tuesday of the following week. We could do it that way. Then the following week after that, we will do a group work review on the last day of class, which would be that following week. The last day of class is Tuesday. So that'll be your last day of class. We're going to do a review for the final. And then the final exam is going to be available for 2 days. Now, if I were to look at the exam schedule, the final exam schedule says for classes that meet on Tuesday and Thursday at the time that we meet, which is at 9:30. Now, see, they're going to screw us up. Oh, yeah, they're screwing us up. That our final exam is on Tuesday morning, and we have to have the grade. And by Tuesday afternoon, if we haven't gotten the grades posted, they start texting you or they start emailing you saying, because the grades have to be due the next morning. Oh, that's a sucky thing. I think this is what I'm going to do. The test will be available from Monday to Tuesday. And I think, see, it says I'm kind of limited because I don't want to have it where you have your final exam due at the same time all your other classes are due. So this is why they break it up like this. So if you were taking seated classes, they would be all done on at different times. So they've allocated that our final exam, if you were coming in to sit down and take it, would have to be on Tuesday, May the 11th, from 8 o'clock to 10. Now, you do not have to take it right at that time. So the way I think I'll have to do it is that it'll open Monday morning, because they do not allow me to do it over the weekend because of the help desk being closed. So it would open Monday morning, but I think it's going to need to close at 10 o'clock on Tuesday. So you could take it on Monday, you could take it Monday night, you could take it in the middle of the Monday night, early in Tuesday morning, or you could take it from 8 to 10. But I think what we need to do is have it to close at 10 o'clock on Tuesday. Then that allows me to get the grade posted in time so that administration's not going, where's the grade? Where's the grade? They actually start publishing a list of all the courses that haven't yet had their grades posted. But then they put it where you're still giving final exams on Tuesday if you do it. So it's kind of crazy. So anyway, that's the deal. So consequently, I'll put that there. So this is going to be on the 11th. So it's going to be, let me go ahead and put that there so we won't, so everybody knows. So I'm going to say the final exam. We're going to say opens Monday, May, and this would be the 10th, and closes Tuesday, May 11 at 10 a.m. Okay. So you've got a window of time of early Monday morning till, well, I'll put it at 8 o'clock on Monday because you got to have the help desk open. Otherwise, it's kind of, so Monday, 8 a.m. All right, does that make sense? So you've got from Monday morning all the way through to Tuesday at 10 o'clock to take the final on your own time. It will use the webcam, and I'm going to have it put in there that says students need to be able to look down, work on their calculator, work problems on scratch paper, and are allowed to use some formula sheets and your trig table and your unit circle and any of the others that I have put here, like your conic section formulas. Any of that you're going to be allowed to use. Those reference forms you're going to be allowed to use on your test. Okay, so that is what we've got going on. Anybody else? Anybody have any questions? Okay, so today I asked y'all what your major is. And you may have heard me mention before, I always try to keep in touch with students that go on to the university particularly if they're in engineering, because I'm an engineering advisor. And one of the ones that stuck out to me this past early this semester is a student that he got his 4-year degree in electrical engineering. And then he started graduate school at South in electrical. And while he was doing that, he got hired with the Space Force as a master electrical engineer. So then they transferred him to Colorado Springs, Colorado. And so he started finishing up his master's there in Colorado at the university there. But what he told me was he showed me pictures where he saves all my notes. So if I were you, it would be good for you to download the PDF of all the lectures, because and print them out if you want, or just have it on a thumb drive. He still uses them and he goes back. But for all of these years while he's been at the university, finishing up his electrical 4-year degree and then starting his master's in electrical, one of the things that they have to do is take a complex number and raise it to an exponent. So let's say we have the complex number 4 plus 5i, and we wanted to square it. Now that's not too hard. So when you square a binomial, I would say that's 3 plus 5i times 3 plus 5i. And so if I FOIL that, first, outer, inner, last, this would be 3 times 3, which is 9. Then the outer would be 15i. The inner would be 15i. And the last would be 25i squared. But I squared, if you remember from your algebra, pre-cal algebra class, I squared is rational. I mean, it's a real number. It's not an imaginary. I squared is a -1. So this would be plus 25 times a -1. So there'll be a minus 25. So what now I have is 9 subtract 25, and I've got my 15i plus 15i. And so what we end up with is the complex number, go down 5, go down 4, so that would be a -16 plus 30i, because the two i's are like and they add together. So that takes me a little bit of time, but it's something I could do pretty well. Now, but what if they said this? Well, that means I have 4 of those multiplied together. So I could think of it as I have this times this. So if I was going to take a shortcut, and I know the answer to that, so that would be like a -16 plus 30i, because I've already figured out what the squared was. This would be a -16 plus 30i. And then I do first, outer, inner, last, -16, that'd be 256. And then my inner. Now, and my outer. So we've got a -16 times 30, which I think is a -480, but let's see, I don't want to do it wrong. Yeah, it was 40. So a -480i, and then the inner would be a -480i, and then the last two would be a plus 900i squared, but I squared is a -1. So this is like saying 256 minus 900. So 256 minus 900 is a -644, and then we add 480 and 480, and we get a minus 960i. So again, we come up with a complex number. But what if you were being asked to raise this to the 12th power, or let's say the 20th power? Now you're getting into this thing that I'm like, okay, this is getting a little much more than I need. But he was a very dedicated student, so he would take the time to do it, and he would work, and he told me that they were always having to do this with some of the stuff they were doing, and he just would work it out in his problems, and it'd take a long time to do it, but he needed to get the answer, and so he would do it. And then somewhere along the way, I don't know what triggered this, maybe another student or an instructor mentioned it, but they said, you've been doing it the long way. You know, there's a shortcut to doing this. And he went back and looked at my 113 notes from years before. And sure enough, there it was, the shortcut for raising a complex number to a power. It's going to be a quick way that you can do it. So for those of you that, particularly Braxton and Keontae, you might have to deal with this in the future. Chelsea and Lindsay, I don't think y'all will. But you do have to have it for this class. But you never know. You may change your major. You never know. So, you know, it might happen. So let's look at a shortcut. So with that little introduction, we first have to learn, how do I put a complex number in what is called trig form? And it's going to be real obvious when you convert it. You're going to have a tendency to want to unconvert it. So we're going to talk about, don't do that. Leave it in trig form. And then we're going to then do DeMoivre's theorem, that is the shortcut. We convert that complex number to trig form. And then if we want to raise that to a power, there's an easy formula for doing it. So to convert it to trig form, I'm going to first, so my complex number is in, the generic form, a plus bi. Now, there's nothing to say the b has to be a plus. It could be, you could have the number 4 minus 7i, right? I mean, but this is our generic a plus bi. So trig form, it looks like this. And so I think, well, how do I get it into this form? Well, first of all, you're going to take the coefficient, your a, which is the real part of the complex number. Remember, a complex number is really a hybrid of a real number a plus an imaginary number b. The bi is imaginary, but we want to just use the b. So this r here it's like taking the magnitude, really, of a vector. I'm going to take my a and square it. I'm going to take just the b, not with the I, just the b, and square it, and add those two numbers together and put them under a root. And that's what's going to go there. And again, if we end up with something that's not a perfect square, we just want to leave it as a root. Don't convert it to a decimal. Now I'm going to say the cosine of my angle plus I times the sine of the angle. So how do I come up with the angle? I'm just going to put the b over the a. So this is kind of like how we converted from rectangular to polar. We're going to put the b over the a and going to find the inverse tan. And that's going to give us the angle. So I'm going to put the b over the a. And I'm going to need the right quadrant again, because you're just going to look to see what would that quadrant be if I were to graph the a and the b. Okay, so let's do an example. Convert the complex number into trig form. So we have 2 subtract 2i. So my a will be 2, and my b, we want to include the negative, will be a negative 2. So how do I first find the r? Well, I square them both and add them together, and I get the square root of 8. Now I put the y over the x, and I'm going to look at the table for the inverse tan of a negative 1. Now, it's important because, again, I have 2 choices. Do I choose the angle 3 pi over 4, or do I choose the angle 7 pi over 4? Well, I go back to what these numbers A and B are. If I were to graph that as an ordered pair, what quadrant would that be in? The x, think of this as your x is positive and your y is negative. Well, that would be quadrant 4, right? So I'm going to come over and find the angle in quadrant 4 where the tan is a negative 1. And so that's going to be 7 pi over 4. And so then I just put it in the form. The form was, I put the r first, and then I say the cosine of that plus I times the sine of that. So now I have converted 2i, 2 minus 2i, into complex form. Now let me tell you what the tendency is. The tendency, because we're so used to evaluating the cosine at that and the sine at that, the tendency is to simplify this. But guess what happens if I simplify that? I undo it being in trig form and it goes back to being like that. So we don't want to undo that. You just want to leave it like that. Now, sometimes people will say the square root of 8 is the square root of 4 times 2, which is the square root of 4 times the square root of 2, which is 2 root 2. So either one of these is a correct answer. And if I were to go to my trig table and find this value and find this value, and then multiply by this, you'll get right back to what you started with. So don't undo it because we got it in trig form. Now here's another one. Convert this to trig form. It's a complex number because it has our I. So I'm going to, my A is root 3, my B is 3. I'm going to square root 3. And when I do, I just get 3. And I'm going to square my 3 and get 9. So 3 plus 9 is 12. So my R is the square root of 12. And if I put it to its principal root, 12 is 4 times 3. The square root of 4 is 2. So 2 root 3. Now I need to go to the quadrant. So what quadrant would you be in if the A is positive and the B is positive? That is quadrant 1. So I'm going to go to quadrant 1, and I'm only going to use the angles in quadrant 1. So it says, take your B and put it over your A. Now, the biggest problem with this is I'm looking, and I don't see it where I have a 3 over the root 3. That's because these have already been rationalized in the table. So I'm going to rationalize that. I'm going to say root 3 over root 3, which is 1. I'm allowed to multiply by 1. This will be 3 root 3. This will be root 3 times root 3 is 3. The 3's cancel out, and this is just the square root of 3. So I'm looking in quadrant 1 for square root of 3. So I focus only on quadrant 1, and because of the A and B both being positive, and I find my square root of 3, It is pi over 3. So my angle that I'm going to use is pi over 3. So once I've calculated R and Q, I just substitute them into the formula. So my R is times the parentheses of the cosine of pi over 3 plus I sine of pi over 3. Or for those overachievers out there, you can change the square root of 12 to being 2 root 3. Now I'm kidding about you being an overachiever, but either way, these are both correct forms. Okay, so now we've got that same complex number, but now it's being represented in trig form. Let's look at another example. A negative 3 plus root 3i. Okay, so to find R, my A is a negative 3, my B is the square root of 3. I square the A and I get 9. I square B and I get 3. I add them together, same thing, root 12 or 2 root 3. Now the angle's going to be different because this time we put the root 3 on the top and we put a negative 3 in the denominator. So I'm looking for the angle. Again, you're going to have two options. So I want to make sure I pick the right angle that matches the quadrant that my point is in. So if I were to think of this as my x coordinate being a negative, and this being like my y is a positive, negative x, positive y, that's quadrant 2. So that's a point in quadrant 2. So I'm going to focus on only on quadrant 2, and I'm going to look for a negative root 3 over 3. And here it is, and my answer is 5 pi over 6. So once I've done those, I just plug it in where the angle is 5 pi over 6, and this R value is root 12, or I could put it as 2 root 3. Anybody have questions on that? So we just did a number of examples of different ways that things could show up. Now, how would I go back from trig form to regular form? That would be where you would just simplify this. This is why I was saying leave this like this, because if you simplify it, you undo what you've just done. So I just go to my trig table and I find the cosine at pi over 4. So the cosine at 5 pi over 4 is right there. So the cosine is a negative root 2 over 2. The sine is also a negative root 2 over 2. But don't forget there is an I here. So I've got 4 root 2 times a negative root 2 over 2 minus a root 2 over 2i. Now I just distribute this 4 root 2. When I distribute this, this will be 4 times 2, because root 2 times 2 is 2, divided by 2. And I distributed this to this, and I get root 2 times 2 is 2, times 4, divided by 2. And then what you see, this is 8 divided by 2 is 4, and 8 divided by 2 is 4, and this is a negative, and this stays a negative, and there's your complex number back. So that's how, you just distribute, you just go to the trig table and then distribute, and then you get back. This is why I was saying, once you put it in trig form, don't simplify it, just leave it like that. Now, DeMoivre's theorem is going to be that shortcut to raising a complex number to a power. By the way, it's kind of like when we raised, I don't know if you were taught the binomial theorem in, if you took 112 or you took pre-cal algebra, wherever you took it, there is a shortcut using the binomial theorem to raise a binomial that doesn't have I in it. It's just a binomial, like maybe it's like 2x plus 5. You want to raise it to the 10th power. That would be pretty hard to do by hand, take you a long time, just tedious, really. But with the binomial theorem, you could do it pretty quickly. Well, this is similar. It's going to make it easier. So here's the theorem. So I've got my complex number written in trig form, and I want to raise it to some power. And they said the way that you can do it is you're going to raise your R to that power. But notice you're not raising the cosine to that power. You're multiplying the exponent to the angle of the cosine and to the sine. And that's how you go about doing that. So let's look at some examples. And in fact, what we'll do is we'll finish up by using that problem that we made up on the side and showing that I could do it quicker if I, then the long way to the 10th power by using this right here. Okay, so let's do this now. So it's not hard. If I were just raising something to the 2nd power, I wouldn't use DeMoivre's theorem, because it's just real easy to FOIL. It just means I have 2 of these, and I can just FOIL first, outer, inner, and last. And I get 25 plus 50i plus 25i squared. And then remember that I squared is a -1, so that would be a -1 times 25. So I've got a 25 minus 25. And it's not unusual with these that you end up getting something simple, like just a number or 50i. So like in the 2 examples that we did when we FOILed it, we ended up with still 2 terms in our complex number. But a lot of times it's not unusual to end up with just a constant or just the imaginary part. It happens. So don't think you did something wrong if that happens. If I was going to do DeMoivre's theorem, if I was raising a 2nd power, this is like more work. I think I'd do it the other way. But if I get to an exponent higher than 2, DeMoivre's is going to help. But if I wanted to show you get the same answer, because if you give me one that has a large exponent, I'm not going to do it the other way to show we get the same answer. That's too much work. All right, so I've got my A plus B. So my A is 5, my B is 5. That's quadrant 1. Those are both positive, so I'm going to have a quadrant 1 angle. And so all it said to do, remember, was take your A and B and square them. So 25 plus 25 is going to be 50, the square root of 50, or 25 times 2 is 5 root 2. Then I put the 5 over 5, and I get inverse tan of 1. And again, this is quadrant 1. The A and B are both positive, so I just look in quadrant 1 for 1, and I get pi over 4. So in trig form, this is root 50 times the cosine of pi over 4 plus I sine of pi over 4. Now we're going to use DeMoivre's to raise it to the 2nd power. Our 2nd power is 2. So n is 2. So we're going to raise this r to the 2nd power, but I'm going to multiply the angle of the cosine and sine by 2. And I get pi over 2, because 2 pi divided by 4 is pi over 2. That reduces to pi over 2. And the root 50 squared is just 50. Now the cosine at pi over 2 is, I go to pi over 2. The cosine at pi over 2 is 0. The sine at pi over 2 is 1. I multiply 50 to both, and I just end up with 50i. So notice I do get the same answer. But again, I don't think I'd take the time to do this if I was just raising it to the second power. However, if I'm raising it to the 8th power, oh yeah, I'm going to use DeMoivre's. It's a French word, by the way. That's why it's kind of pronounced kind of in an odd way to our ears, not odd to the French. Okay, so that means I have 8 of these multiplied together. And I know what the first two are. They're 50i, and this two are 50i, and this two are 50i, and this two are 50i. So there would be a way we could, kind of do that. There's some shortcuts a little bit in doing it the expanded way. But still, it's going to be easier to use DeMoivre's to an 8th power. So we've got our trig number. We've got our complex number in trig form. Now to raise this to the 8th power, I raise the r to the 8th power. And then I multiply the angle of sine and cosine by 8. This becomes 2 pi. And this is 2 pi. So I go to my trig table and I find 2 pi. The sine at 2 pi is 1. No, the cosine at 2 pi is 1. The sine is 0. So this is going to be 0 times I, which will be 0. And this will be 1. So now there's a shortcut even here. Let's say you didn't have a calculator. 50, the square root of 50 is 50 to the 1/2 power. Now, your laws of exponents say when I multiply the bases, I add the exponents. When I have a number raised to a power, which is also raised to a power, so a power raised to a power, I multiply my exponents. That's going to be 4. 50 to the 4th power is this big number. So this is the answer you get by using DeMoivre's. So let's do the problem that we were just doing with the 10th power, or I got 12th here. And let's see if we can do this problem, raising it to the 5th power with DeMoivre's theorem. So the first thing I want to do is get this in trig form. So the first thing is r is going to be the square root of 3 squared plus 5 squared, which would be 9 plus 25. I don't want to mess this up, so I'm not going to do it in my head. 9 plus 25 is 34. So it's the square root of 34. Now, for the other, theta is the inverse tan of your b over, okay, this one is a little bit bad example because that is not a standard trig value. But you could use, I guess, your calculator. It's not going to be exact, though. This isn't the best example. Let's do one where I want to change that up just a little bit so it is a better example. So our trig values that we're wanting to come up with, let's just say this is also 3. I'm not going to give you one where you don't end up with a standard angle. So this would not be that. This would be 3 squared, and this would be something else. So this would be 3 squared, 9 plus 9 is 18. All right, so in trig form, this is the inverse tan of 1. So now I need to know my A is 3, my B is 3. That's both positive. So this is a quadrant 1 angle. So now I want to go to quadrant 1 and I want to find when is the inverse tan 1? When is it a positive 1? And that's really on the 45. That's pi over 4. So, but let's go to it and see. So, when is the inverse when is the tangent 1 in quadrant 1? And that's at pi over 4. So we see that theta here is going to be pi over 4. All right, so in trig form, this would be the square root of 18, the cosine of pi over 4 plus I, because you still have your I in there. That's a horrible looking plus sign. But again, and that's not going to be better. Okay, and that's going to be the sine of pi over 4. So I want to raise all of this to the 12th power. So if I'm raising all of this to the 12th power, then I raise the square root of 18 to the 12th power, but I multiply the angle by 12. So this would be the cosine of 12 times pi over 4 plus I sine 12 times pi over 4. That turns out to be pi over 3 pi, right? So 18, this is 18 to the 1/2 power times 12, so it's going to be 18 to the 6th power. 18 to the 6th power is one big giant number. 34 million. 34 million. 1,200,000. 224. Or 12,204. Now, this is times the cosine at 3 pi. Now, what was 3 pi? It's bigger than 2 pi. So one rotation is 2 pi, right? One revolution around the circle. So I'm going to subtract 2 pi to get it down below 2 pi. So this is 34,012,224 times the cosine of pi plus I sine of pi. All right, so let's go look at the table and see what is the cosine at pi. The cosine at pi is a -1. The sine at pi is 0. So this would be a -1, and this would be I times 0. So that's going to be gone. So I've just got a -1. So the answer of all of that is that. There's your answer. So, I mean, it took a little bit of work to get this done, but it didn't take a lot of work to get that done. I mean, in terms of what you'd have to do to multiply that, if you had 12 of those parentheses multiplied together, that'd be a lot of work. I wouldn't want to do it that way. So DeMoivre's is your shortcut. Okay, so we have now covered all of the chapter for chapter 7. Now, where we go next is conic sections. Conic sections are, they show up a lot of times, and there are 4 of them. One is a circle, one is an ellipse, one is a parabola, and one is a hyperbola. And because all of these, except for the parabola, they're not functions. So graphing in the calculator is a little bit hard. So how do we even get conic sections? I had a teacher in high school that she would teach conic sections. And I remember she would get out she had up there, and she kept it on top of her cabinet, but she had gotten these were made of wood, and she could take it apart where it was like a visual, it was a visual aid. But what you could physically see, that if you took a knife where this had been cut with a saw so that it went straight across there, parallel to the floor. When you opened it up, it's kind of like that thing. If you cut an apple a certain way and open it up, you see a star. Well, same thing here. When you cut it and you open it up, what you see is a circle. That's how you get a circle. That's why a conic section is a circle. But let's say that I couldn't quite get it parallel to the floor, and I ended up getting it kind of skewed. Well, it's going to make something that looks like a circle, but it's going to be elongated. And it's what is an ellipse, which is a circle somebody sat on and made it kind of elongated. And it can elongate along the y-axis or along the x-axis. So it depends on which way it elongates. Now, another thing you could do is if you took a saw and you cut it at an angle, like now this was an angle where you were above the base, so it still made a circle. But what if I took an angle? By the way, these are two cones. That's why conic comes from the word cone. Two cones, one's inverted, the other is upright. If I cut it in such a way that I hit the floor with it, it actually makes the shape. If I then took it apart and showed you, it makes the shape of a parabola. And then lastly, what if I took the saw and just went straight down with it? Well, I would end up with a parabola on the top, but I would also end up with a parabola on the bottom. So those two parabolas together, one on top of the other, one facing up, one facing down, is a hyperbola. So the hyperbola is like two parabolas combined from the conic sections. So one of the things that we're going to be looking at is, and this is to me the most important thing when you're looking at these, is if I had an equation, how do I know whether it's a circle or an ellipse, or whether it's a parabola or a hyperbola? And there's some basic ways that we can know. But first of all, this is really the kind of form they tend to put it in, where they have a 1 on the right side, and then they have these x squares and y squares divided by a number. Well, how could I get it back into another format to make it easier to understand what do I have? I could multiply every term on the left and right side by 9, and it would put it in this form. Now, multiplying this by 9 wouldn't get rid of the 4, and multiplying both of these by 4 wouldn't get rid of the 9. But if I multiply both of them by 9 times 4, 36, it will get rid of the fraction. So I'm going to multiply this by 36, this by 36, and the 1 by 36, and I get this. Same thing here. I'm going to need to multiply both terms on the left and the term on the right by 36, and I get this. And I'm going to multiply both of these by 4 and the 1 by 4, and I get this. Now let's see if we can recognize how could I just look at this and know this is a circle? Well, first of all, it has an x squared and a y squared. And you're like, yeah, and so do the ellipse, and so does the hyperbola. But it's all now about the coefficients. it has an x squared and a y squared, and the coefficients of the circle will always be the same number. So this is a positive 1, and this is a positive 1. That's how I know it's a circle. Now, an ellipse will look just like a circle, except the coefficients will be different. One, you've got a 9 and a 4, not the same. That's an ellipse. Now you say, but a hyperbola, well, the difference with the hyperbola is that one will be added and the other will be subtracted. So they're not going to, even if you say, well, they both have a 1, I'm going to say, not really. The y has a coefficient of -1. So a hyperbola will always have one being added, one being subtracted, the x squared and the y. The parabola is the easiest one to recognize because you will not have both an x squared and a y squared. So like one, you might have an x and a y squared, or you might have a y and an x squared. And that's a parabola. If the y is squared, it's a sideways parabola. If it's an x squared, it's up and down. So what we're going to do when you come back, we're going to focus in on each one of those now that I've mentioned how you can recognize them. And we're going to look at some things about recognizing circles. I'll talk more about that. And looking how maybe to graph them, how to get an idea about what to do with that. So I wanted to introduce you to the conic sections, and then when you come back on Tuesday, we're going to finish up the conic section, and we're going to be able to then go into the review for chapter 7 and 10. Okay, so any problems with that? Everybody okay? Everybody okay with that? You know what's going on? All right. Well, I hope y'all have a good weekend. I think the weather's going to turn weird on Saturday. I think it's stormy on Saturday. Oh, the last I heard it was. So, and that's our weather report for today. Have a good weekend, regardless. And I'll see y'all back on Tuesday.